In this section we're going to be looking at the ratio test, the root test, and then two tests of comparison called limit comparison, and then I like to call it the direct comparison, or also known as the comparison test. And all of these are tests for positive terms. Infinite series basically is what we're looking at. So again, what we have are more ways to test more series. Now when we're looking at the ratio test, one thing I'd like to note is this is really nice for working with factorials. So if you see an expression with a factorial in it, it may be that the ratio test would be a good test for you to use. So just a quick review over factorials. 5 factorial is 5 times 4 times 3 times 2 times 1. That's the definition of our factorial. 1 factorial is just 1. If you happen to come across 0 factorial, that's also defined to be 1 as well. Now when we're working with variables, if you have something like n factorial, that's going to be n, n minus 1, n minus 2, etc. If we have something like n minus 3 factorial, actually let's start with n plus 3 factorial. That would be n plus 3, n plus 2, n plus 1, and then n minus 1, etc., but this is just n factorial again. So if you had something like n plus 3 factorial over n factorial, what you could do here then is you could realize that as the larger factorial counts down or factors down, these will eventually cancel and simplify. Another thing that we might come across is we might have something like 2k quantity factorial. Okay, this is going to be 2k times 2k minus 1 times 2k minus 2, etc. Now a lot of times we end up plugging in a k plus 1, so that would look like 2 times k plus 1, all of this quantity factorial. It's not, wouldn't be just the k plus 1 that's the factorial. So simplifying, this would look like 2k plus 2 factorial, which is 2k plus 2, 2k plus 1, 2k, and if we wanted to write that, that's 2k factorial from there. Now, one quick note, 2k factorial does not equal the quantity 2k factorial. Now, these will all be clear when we start writing out some of these tests. So, let's go ahead and write out what the ratio test actually is, the specifics of it. So, for the ratio test, we have some sort of a sequence producing function. So let's let the series a sub k be an infinite series, and that's what all of these are that we're looking at in this particular section, are infinite series, and it only has positive terms. Now if we say positive terms, that means there's no zero terms either. And this is the important thing about the ratio test. And what we're going to do is we're going to let r standing for ratio in this particular case, equals the limit as k approaches infinity of a to the a sub k plus 1. So this would be the next term, make that look like a k, divided by a sub k, which is our current term. Now there's three things that can happen from this. When we take this limit, one thing that could happen is this value of r that I get is somewhere between 0 and 1. Notice 0 is equality here, r is just less than 1. If this is the case, the series converges. Okay, our other case that we'd look at second would be if r is greater than 1. Now r is greater than 1 includes infinity. So if we get a limit that's infinity, I'd be in this case, we would get that the series diverges. Okay, so the only case that we haven't covered is the case if r equals 1. And if r equals 1, this test is inconclusive, and I would have to try some other test. So let's go through a quick example of a problem that we could look at using the ratio test, and then we'll look at some other tests as well. Now I mentioned that using the ratio test, if we see a factorial, the ratio test is a good one to use. That doesn't always mean it's true. We usually start with the nth term test for divergence or the test for divergence, And if the test for divergence fails, then we can try a few other things. But if you see a factorial, usually it's a pretty good thought that the ratio test is going to work here. So first of all, what we need to do is name our test. Second thing we do is we actually perform the test. Now to perform the ratio test, what I need here then is the limit as k approaches infinity of the next term. So that means all the k's become k plus 1. And this becomes k plus 1 quantity factorial. And then I divide that by our current term. So if we look up here, I'm writing this as a fraction. So up here you can see it's written as a fraction. But remember, when you divide by a fraction, you're actually multiplying by the reciprocal. So I'm going to go ahead and write this, and then from here on out we'll probably just flip it right away. And then we divide it by our current term, 9 to the k over k factorial. Well, the whole idea is we'll be able to simplify this in order to take a limit. So this would be 9 to the k plus 1 over k plus 1 quantity factorial. And again, when you divide by a fraction, you multiply by the reciprocal. And then we want to simplify this. Now if we start simplifying this, first of all, 9 to the k cancels with this 9 to the k, leaving me with the 9. And then k plus 1 factorial is k plus 1 times k factorial. So these k factorials cancel, and I'm just left with 9 over k plus 1. Now when I take my limit here, this is going towards 0, and we need a reason why, because the degree in the numerator is less than the degree in the denominator. Now if we look at our rules, if we have, remember this is our value for r, is this limit. So we get that r equals 0, which is definitely going to be less than 1. So therefore, for this particular instance, this would converge. So again, name the test, go ahead and show your work performing the test and the simplification, draw your conclusion. I have to say, I can't just say r equals 0 so it converges. I have to say why, because it's less than 1. Okay, and that's this first case. It's definitely less than 1, so it converges. So that's an example of using the ratio test. In this specific case, we use factorials as well. Now sometimes you'll run into a problem in this particular section where you're asked to force something to converge. And it's actually a little bit different setup of a problem, but it's still using the ratio test. So for this one, if you'll notice, this one's a little bit different. K equal 1 to infinity. We're looking at x to the k all over 2 to the 2k. Now the couple things that I look at on this one. First of all, we have a value of x here, so depending on what x is, this could converge or diverge. So I'm trying to force this to converge. So I am trying to find the values of x that will force this to converge. So find the values of x. And in this particular case, for which the series converges. Okay, so in this particular case, it looks like we could just run through the ratio test, and then at the end we'll force it to converge. So for the ratio test, I look at the limit as k approaches infinity of the next term, so all of my k's become k plus 1s. Now this isn't just 2k plus 1, it's 2 times the quantity k plus 1 divided by my current term. But when you divide by a fraction, you multiply by the reciprocal, so this pops up top, x to the k. And again, I want to simplify here. Now if you've had Calc 2 before and you've worked with some of these tests, some textbooks, and I like how the other textbooks do this, they talk about the ratio test as a test of absolute convergence. And then we get to talk a little bit more about these intervals of convergence, IOCs, but we'll get to see that a little bit later on in this section. So as we simplify this, I'm going to write a little bit more out. This is x to the k times x to the 1. In our denominator here, this would be 2 to the 2k plus 2. So this would be 2 to the 2k times 2 to the second. And then over here I have that 2 to the 2k and then x to the k. So x to the k's cancel, 2 to the 2k's cancel, and it looks like to me that we're left with the limit as k approaches infinity of x over 2 squared, which is 4. Now remember, this is my value for r. There's no k here. So this is just a constant. So the limit of a constant is just a constant. So what I get here is that r is equal to x over 4. Now if I want to force this to converge, I basically say, I look up at my rules, and it will converge if it's less than 1. So let's go ahead and force this to be less than 1. And what I did here is I forced convergence. And then to solve for x, I go ahead and multiply both sides through by 4, and I get x is less than 4. So this is the interval for values less than 4 that will force this to converge. And we won't run across too many of these right now in this particular section, but it does come up. We'll see these a little bit later on, probably more towards Unit 4 if we see them at all. Now when you're using the ratio test, a lot of this is just simplification, and a lot of it. You have to make sure you show your work. You have to break down the steps. You don't want to skip any steps, and sometimes you might end up using L'Hopital's, or sometimes you might actually end up using that idea of taking a log of both sides of a particular expression in order to find the limit. So don't give up on these, and make sure you show a lot of work, and make sure you justify all of your steps, and definitely don't skip any steps. Let's go ahead and look at the root test next. The root test is similar in our list as the ratio test in terms of what happens when we have the different values of r. But what the different part is what these are good for, what they're handy for. The root test is really nice if we have expressions that are raised to powers. So for the root test, let's go ahead and look at a series. So let's let a series a sub k, sorry, I'm so used to using n's for mine, series a sub k be an infinite series again. And as usual, like our last one, we have non-negative terms. And I think our last one, when we talked about it, we specifically said positive terms, but this one we're saying non-negative. So this could include 0. And so what we want to look at here is we want to look at, instead of r, we're going to be looking at rho. So this is Greek letter rho. Kind of looks like a P. I should be careful how I write that. But this is Greek letter rho equals the limit as k approaches infinity. And this would be the kth root of a sub k. Now what happens is this a sub k has an exponent that's a k, and so the k's end up canceling or simplifying. So if this is the case, I have 3 different outcomes, same as I have for the ratio test. If I have that rho is between 0, equality at 0, and 1, then what happens here, the series converges. Second case, if I have rho is greater than 1, and this of course includes infinity, the series diverges. Third case here, if rho equals 1, just as above, the test is inconclusive. Okay, so let's go ahead and look at a problem where we have the root test. And again, the root test works really nice for expressions or series that have an exponent of some sort that I'd want to clear out. It could be a k to a power, for instance. Okay, let's go ahead and look at k equal 1 to infinity. In this one, I'll have 1 plus 13 over k to the k squared. So this is a pretty typical example. If you notice, I have this k squared in my exponent. So I would want to take this and I would want to use the root test on it. So as usual, we name our test. And then I take the limit as k approaches infinity. And I'm not going to do the k squared root. I'll just do the kth root of this expression. So as we simplify this, this is the limit as k approaches infinity of 1 plus 13 over k, and then k squared over k would just leave me with a k. Now this should look pretty familiar. This I can't take the limit of right now. If I do, I would get 1 to the infinity, which is an indeterminate form. So I'd want to use logs. So what I do here then is I go ahead and set this equal to y and then take the natural log of both sides. Now the whole idea of taking the natural log of both sides is so I can get that k out of the exponent. Now if I take my limit right now, I'd get infinity times 0, which is indeterminate. So I need to rewrite this into an indeterminate L'Hopital's form. So indeterminate L'Hopital's form, I need a numerator and a denominator. And again, we've looked at these types before, so this is kind of a familiar idea. Times 1 over k. Now remember, if I flip this k up top, it would be right here in the numerator. So this is just a nice way to rewrite this. Now if I take my limit, I would get 0 over 0, which is now an indeterminate L'Hopital's. And then I can work through the problem using L'Hopital's rule from here on out. Okay, so the derivative of the natural log of u, this is applying L'Hopital's, is 1 over u, 13 over k. Should make that look like a k. Times the derivative, so it's 1 over u times the derivative of 1, which is 0. The derivative of 13 over k, I'd pop the k up top, that'd be k to the negative 1. So it'd be a negative 13k to the negative 2, or negative 13 over k squared. The derivative of 1 over k is negative 1 over k squared. Okay, so simplifying, we have quite a bit here to simplify. I have this negative 13 over k squared. Now remember, when you divide by a fraction, you're multiplying by the reciprocal. So this negative k squared pops up top. And then of course I can simplify quite a bit from here. So the k squareds cancel, and negative times a negative is a positive. And it looks like I'm going to be left with the natural log of y equals the limit as k approaches infinity. Looks like we'll have a 13 left on top, 1 plus 13 over k. Now as k goes toward infinity, this goes towards 0, and I'm left with the natural log of y is equal to 13. Now let's remember what we were trying to do. It seems like a long time ago, but we're trying to figure out what rho is. So what we get here is e to the 13th equals y. And this whole idea was to figure out what rho is, and in this case rho is equal to e to the 13th. So e to the 13th is a very, very large number. So this is greater than 1. So therefore, because it's greater than 1, what ends up happening here is the series diverges. And again, by the root test. So these can be pretty long problems, but most of the work here we've done before in terms of finding that limit. And again, you don't want to skip any steps or skip any simplifications. All of those steps need to be there in order to earn your full credit. We don't want to skip anything. The next step, or the next test that we want to look at, is called the comparison test. And there's two comparison tests. The first one is they just call the comparison test, and I usually refer to this as the direct comparison test, just to distinguish it between that and limit comparison. Now I'm going to write this out formally, and then I'll kind of give you some shortcut ways to try and remember what's going on here. So the comparison test starts out with two series. One series is a sub k and the other one is b sub k. So let's say we have two series, a sub k and b sub k, and they have positive terms. Now what happens with these series with positive terms are two things. First of all, if we can write our inequality, and this is a little bit confusing to me the way that they write this, so I always have to rewrite it in some terms I can understand. So basically positive terms, so that's why I have my 0 here. A sub k is always going to be less than or equal to b sub k. So a sub k is the smaller in this case, b sub k is the larger. And what we know, if this is the case, and we also know that the series b sub k converges, then what ends up happening here is a sub k converges as well. Okay, so like I said, this confuses me, so I have to write this out. So what we get here is the larger series converges. And so it totally makes sense if the larger series converges that anything less than that would converge as well. So the larger series converges implies that the smaller series converges. So that's how I remember these, is in terms of larger and smaller. Now there's another case that occurs here too. A little bit confusing the way they write it. This time they switch around the b sub k and the a sub k. And they say in this particular case b sub k converges. And then the result then is that, I'm sorry, diverges. We already did converges. Then what we have here then is a sub k diverges as well. And again, these get confusing because they switch the order of a sub k and b sub k, so I always have to rewrite these. So b sub k in this case is the smaller one. So what this is saying is if we have the smaller series diverging, then it only makes sense, implies that the larger is a sub k in this particular case, series diverges as well. So if we have a small series and it's already going off toward infinity, it only makes sense that if we have a series that's all terms larger than that it would diverge as well. Now, the tough part about the direct comparison is to try and come up with the series to compare it to. These are not easy because you have to kind of sometimes go by trial and error to find a comparison series. So let's go ahead and look at an example, and we'll give you some ideas about what we could choose for comparison series. It doesn't always work. Sometimes it's easier to go with another test, but let's go ahead and have a look. Now if I want to use direct comparison, I need to know something about larger and smaller, and I need it to fall into one of these cases. Either the large converges or the small diverges to get started. So when I look at this particular series, I look at this and I think, what could I compare this to that would allow me to come up with a comparison for large and small, and then also I need to be able to figure out what's going on with the series that I select in terms of converging and diverging. Actually, I'm going to change this. I'm just going to put a 1 up here to make this one a little bit easier to find a comparison point. So I'm going to use direct comparison, or if you want to just call it comparison, you can, but be aware that we're going to learn another comparison test and they can get confusing. So that's why I like to call this one direct comparison. So sometimes trial and error, I don't know what will work, so we got to try something. So I want to compare this to 1 over k to the 8th. Now the reason I chose that is if we look at just k to the 8th plus 4 and k to the 8th, they're easy to compare. So let's go ahead and decide what this one is. This one is a p series, so again I have to name the test. I have to give the criteria for the test. This is where p equals 8. So I have a p series with p equal to 8. And it seems like to me if p is equal to 8, that's greater than 1. That's our thing that's important. It's greater than or equal to 1. So this would go ahead and converge. Because p, my value here, is greater than or equal to 1. So now what I know is I know 1 over k to the 8th converges. So now I need to look at this and think larger and smaller. And these are the words that you want to have involved in this, larger and smaller. Now if I look at this ratio, the ones are the same, so I can't compare the numerators, but I can compare the denominators. This denominator on the right, or sorry, on the left, k to the 8th plus 4, is larger than k to the 8th, but because it's in the denominator, it makes the overall fraction smaller. So our overall fraction will be smaller there. So this is going to be my larger, and this is going to be my smaller. And this is the way you kind of want to logic your way through these. So what we know then is the larger is converging. So the larger series, and I'm going to write out what it is. I'm not just going to use the word larger. I'm going to show which the larger is. The larger series converges. So let's see. So we have up here, if the larger series converges, then the smaller series converges. So the larger series converges, therefore the smaller series, and again, don't just write smaller series, write what it is, converges as well. And that's using direct comparison. So again, it's the tough part is trying to find something to compare it to. You want to choose something that's very simple, easy to show which is larger and smaller, and then of course the one that you select to compare it to, you have to be able to look at that and say, oh, I know that this is a p series. This is easy for me to determine what's going on here. And again, it has to fit one of the two scenarios up top. Either the large has to converge to get started, or the smaller has to diverge to get started. So that's an example of the direct comparison or the comparison test. We have another comparison test called the limit comparison test. I like the limit comparison test. It's pretty handy. It might test some of your limit taking abilities. Sometimes they can get pretty intense. So let's go ahead and get started with the criteria. Let's say that we have two series. Again, we'll stick with that a sub k and b sub k notation. So we have two series with positive terms. That means there's no zeros involved here. And what we're going to do is let the limit as k approaches infinity of a sub k over b sub k equal L. Now what this L means, and these are two important words that we need to have, this doesn't say greater than 1. Okay, it doesn't say anything like that. This L value is positive and finite. Those are two things that have to hold true. Okay, now this positive and finite only, I guess we don't need to put in right here, I'll put it in the next step, means something. So when that criteria holds true, then I have one of three things that can happen. The first thing is, if this value of L is between 0 and infinity, and what this means here is that positive finite, so those are the two words I'm looking for here, are both positive and finite, then the series a sub k and the series b sub k either both converge or both diverge. Now one of the things here is I still have to choose a series to compare it to. So that's one of the things we need to keep in mind. So just like direct comparison, I choose the series to compare it to. So I'm either given a sub k or b sub k, and then I have to come up with the other one to make one of these things hold true. Now if I run this test and I get L equals 0, and we know that b sub k converges, what that tells us then is that the series a sub k converges if we get L equal to 0. Now the only case that we haven't looked at here is what if L isn't finite? What if it's equal to infinity? And then our series b sub k diverges. We'll do diverges here because we have infinity. Then what that's telling me is b sub k diverges as well. So there's a lot of different rules we're covering in this section. We have 4 different tests, which is a lot of tests for one section. I think on your note card for the exam, I would be writing down the criteria for each of these tests. I mean, because they're really hard to keep track of and remember which are the rules for each one. So let's go ahead and look at an example where we're using limit comparison. Now, one other quick note with limit comparison, I kind of forget sometimes which is which here. So a sub k is the given series. B sub k is the series you choose to compare. So whatever you choose for b sub k, just remember you have to be able to figure out whether it converges or diverges. Okay, so let's go ahead and have a look. Let's look at the series n equal 1 to infinity. And let's look at something kind of crazy. A rational expression 6x squared plus n minus 7 all over, let's do n to the 4th plus 3n cubed minus 12. Now, the first thing that I would do on this is I would run a quick direct comparison, or sorry, divergence test. If we take the limit, we'd get 0. And of course, that means the divergence test is inconclusive, so that doesn't work. So I'm going to try limit comparison on this. And again, you can try any of the other tests. It doesn't look like a geometric series. It doesn't look like a p-series. So I'm going to try this limit comparison. So we name the test. And then after we name the test, I want to choose what to compare it to. Now this one I don't need to know larger and smaller. Now I want to kind of skip ahead and then come back to what I'm choosing to compare it to. I know that when I take this limit, when I divide by that fraction, I multiply by the reciprocal. So this was my original, and let's go ahead and scroll back up here. It's my original given series that's on top, and on the bottom is what I choose. So when I choose what I'm going to compare it to, when I flip it up top, I want to be able to get something here that I can actually take the limit of. And so that's kind of what we want to focus on. And then once I kind of look at that and decide, then we'll kind of work backward. And I have to kind of choose wisely about this, because if I choose incorrectly, I might get infinity, but what if what I chose converged? Then I have no conclusion here. So I have to be able to work within these criteria. Now when I look at these, I always think about using my shortcut rules, the degree in the numerator and the degree in the denominator comparison. Well, if I think about this as 1 over n squared, what ends up happening is that flips up top. So I'm left with 6n squared plus n minus 7 all over n to the 4th plus 3n cubed minus 12. Now when this flips up top, this becomes n squared over 1. So I'm left with the limit as n approaches infinity. This would be 6n to the 4th, and that's what I was shooting for. That's really what I wanted to have happen here. Now I really don't care about the rest of this because, of course, it's just the highest powers of the exponent. It's in the numerator and the denominator that really matters. So this limit is equal to 6, and the question is, okay, well, why? Make sure you justify that, because the degree in the numerator and the degree in the denominator are the same. Now 6 is not equal to infinity or 0. 6 is equal to, or 6 is between 0 and infinity. So what I want to say here are these two words. It's positive and it's finite. And because it's positive and finite, they either both converge or both diverge. Okay. Well, I didn't ever figure out what it did. Did it converge or diverge? So let's pop that back up here. And that's kind of why I said I want to go here and kind of figure out what happens. And then if it works out to something that's useful, then I'll figure out whether it converged or diverged. Well, this is a p-series, so I need to name my test. P is equal to 2, which is greater than or equal to 1. Therefore, for this particular case, this is going to converge. So it's positive and finite, therefore they both will either converge or diverge, and in this case they both converge because my series 1 over n squared converged. So again, I always have to name the test, and I'm using a test within a test here, so it's kind of getting a little bit complicated, so make sure you organize your work very clearly to show what's going on. So this is an example of limit comparison. Now if I would have chosen, let's say, 1 over n, and this would have flipped up top, I would have gotten 0 out of this. And 0 is okay, except 1 over n diverges. So I would have gotten L equals 0, and my series diverges, and there's no conclusion for that. So I'd have to go back in and try again. So these are an example of each of 4 different tests. And we didn't spend a lot of time going over each test because they're such long problems and we had to cover 4 tests. So make sure that when you're looking through these, that you're looking at specific steps for each one. Now, we have a lot of tests that we've covered. So how do I know which one to use? The first one, this is just kind of my opinion, the first thing I would always do is I would start with the divergence test. If I can take the limit of that and I can get something that isn't 0, then I'm done right away. And taking limits are usually pretty quick. So remember, with the divergence test, we're looking for the limit as k approaches infinity of a sub k, and if we get something here that's not equal to 0, this implies it diverges. Now if it is equal to 0, the only thing I can do here then is to say it's inconclusive, and if it's inconclusive I would have to try another test. So that's what I look for first in the divergence test. Then I look to see real quick, is it a geometric series? Or can I put it in a geometric series form with a quick rewrite? That would make this pretty easy. Another easy one would be a p-series. They're easy to recognize as well. So picking off, kind of like I said, the low-hanging fruit of the geometric series or the p-series would be a good idea. Then what we can do next is you can say, okay, can I integrate it? If it's easy to integrate, then you could use the integral test. But remember, in order to use the integral test, it has to be continuous, positive, and decreasing. And you have to show that. You can't just say it is. You have to actually show it. Continuous, positive, and decreasing. Now, if none of these work, or if you just don't want to integrate it, then what we can do is we can think about, okay, what about any factorials? So if you have anything raised to powers or have factorials, we can try a ratio or a root test. So these would be if we had factorials, powers, meaning we have exponents, let's say like k's, something to the kth power, and then I can take the kth root. That would be something that could work out here. And then, I guess if all else fails, we're at direct comparison and limit comparison. Now the reason why direct and limit comparison are kind of toward the end here, you have to come up with a series to compare it to, and that's sometimes complicated. You can come up with a series to compare it to, but it has to fit all the different criteria that we have going on here. So these can get to be pretty long problems. Now the idea on your handwritten homework or an exam is you don't cross out or erase. I should say you don't erase something you've tried and have failed at. All you can do is put a box around it and an X through it and go on to the next test. You don't want to erase that because that's good work. That's just showing you're trying a lot of different tests. You're just not getting any results. So make sure you name the test, show the criteria for the test, perform the test, and then draw a conclusion about the test. You want to show all of those steps. You don't want to skip any steps, especially if there's integration or algebra and simplification involved. As usual, if you have questions, please let me know. You're welcome to send me a text. You can also set up a time to meet online. You also have the option of the Pearson Connect to a tutor as well. Good luck and have fun with these. They're a little bit long, but stick with them, especially with the simplification, and you'll be fine.